Close your eyes for a moment and listen not to the sounds around you, but to something far grander. Imagine the universe itself humming, a deep, resonant vibration echoing through the emptiness of space. This isn't science fiction, it's a reality hidden in the faint whispers of the cosmic microwave background, the oldest light in existence. What if the cosmos isn't silent? What if, as ancient philosophers once believed, the stars and planets move in perfect harmony, creating a celestial symphony we're only just beginning to hear? 2,500 years ago, the Greek mathematician Pythagoras first proposed the idea of the music of the spheres, the notion that celestial bodies produce harmonies as they orbit, a cosmic melody too vast for human ears. For centuries, this idea lived on the border between poetry and science, a beautiful metaphor with no proof. But today, something extraordinary is happening. Modern astrophysics has uncovered patterns in the cosmic microwave background, the afterglow of the Big Bang, that eerily resemble the mathematical ratios of musical scales. It's as if the universe left us a musical score written in the fabric of space itself, and we're finally learning how to read it. This is the story of how ancient wisdom and cutting-edge science are converging in ways no one could have predicted. We'll journey from the mystical teachings of Pythagoras to the high-tech satellites, mapping the faintest echoes of the early universe, revealing harmonies older than time. Along the way, you'll discover how the universe's first light holds secrets about its birth, and perhaps even its ultimate fate. So if you've ever wondered whether there's music in the void, or if the cosmos has a rhythm of its own, you're about to find out. The universe isn't just expanding, it might just be singing, and this is the story of how we learn to listen. Pythagoras stood on a moonlit beach in ancient Greece, pressing his ear to a taut string stretched between two rocks. As he plucked it, he noticed something astonishing. The pitch changed in precise mathematical ratios when he divided the string. To him, this wasn't just music, it was the hidden language of the universe. If simple vibrations followed mathematical rules, he reasoned, why wouldn't the planets, those colossal celestial bodies tracing perfect arcs across the night sky, do the same? This was the birth of the music of the spheres, the idea that each planet's orbit produced a unique hum, blending into a cosmic harmony too vast for mortal ears. Centuries later, Johannes Kepler, the astronomer who unlocked the elliptical paths of planets, was equally obsessed with Pythagoras' vision. He scribbled musical notes alongside his calculations, convinced that Mars and Earth sang distinct tones as they raced around the sun. In his work Harmonics Mundi, he even assigned each planet a melody based on its speed: Saturn a deep, slow drone, Mercury a frantic high-pitched trill. But Kepler went further than Pythagoras. He didn't just dream of celestial music, he tied it to the physical laws of motion, laying the groundwork for Newton's gravity. His genius was realizing that the universe's harmonies weren't poetic metaphors, they were mathematical truths waiting to be decoded. Yet today, we know planets don't literally whistle as they orbit. The vacuum of space carries no sound, so was Pythagoras wrong? Not entirely. Modern physics reveals a breathtaking twist. His idea of cosmic vibrations wasn't fantasy, just premature. The universe does sing, not through planets, but through the primordial echoes of the Big Bang itself. The cosmic microwave background, that faint glow permeating space, isn't random noise. When scientists converted its fluctuations into sound waves, they found peaks and valleys matching musical intervals, almost as if the infant universe was humming in tune. What connects Pythagoras' string to the Big Bang's afterglow? The answer lies in the language of waves. Just as a plucked string vibrates at specific frequencies, the early universe rippled with density waves, leaving imprints in the cosmic microwave background. Those patterns, frozen in time, mirror the mathematical ratios of musical chords. The ancients sensed the music but lacked the tools to hear it. Now, with satellites like Planck mapping these subtle vibrations, we're finally deciphering the score. The universe may not play Pythagoras' celestial lyre, but its deepest rhythms, written in light, gravity, and quantum whispers, are more profound than even he imagined. Sound is nothing more than vibrations traveling through a medium, air, water, even solid objects. When a guitar string plucks, it pushes air molecules, creating ripples that reach your ears as music. But space, that vast cosmic ocean, is eerily silent. Why? Because sound needs something to travel through, and the vacuum between stars is emptier than any laboratory chamber we can create on Earth. Yet if you could stand in the void near a distant galaxy, you'd witness something extraordinary. Celestial bodies moving with the same rhythmic precision as a symphony's tempo, their gravitational dances imprinting hidden patterns on the universe itself. This is where modern science performs its magic. While our ears can't detect the silent waltz of planets or the groan of colliding black holes, astronomers have found a way to translate the cosmos into sound. They take electromagnetic waves, light, radio signals, even the faint heat of the cosmic microwave background, and shift them into frequencies our ears can process. It's like turning a painting into a song. The process, called sonification, doesn't just make space data audible, it reveals harmonies our eyes might miss. For example, the Chandra X-ray Observatory transformed the Perseus galaxy cluster's pressure waves, ripples in superheated gas, into a haunting bass note 57 octaves below middle C, a tone no instrument on Earth could produce. Now apply this to the cosmic microwave background, that ancient light from the universe's infancy. When the Planck satellite mapped its subtle temperature variations, scientists didn't just see a static snapshot, they found oscillations like echoes of the Big Bang's first vibrations. By assigning pitches to these fluctuations, warmer spots as higher notes, cooler ones as lower, they uncovered something astonishing. The universe's earliest moments followed mathematical ratios eerily similar to musical intervals. A major third here, a perfect fifth there, as if the cosmos was tuning itself. This isn't just poetic coincidence. Those patterns trace back to quantum ripples in the newborn universe, stretched across space-time by inflation. Think of it like plucking a string and watching the vibration slow over billions of years, freezing into the cosmic microwave background's peaks and valleys. The ancients imagined celestial harmonies, but today we're holding the sheet music written not in notes, but in the very structure of reality. And with each new sonification, we're learning to listen to the universe's grandest composition, the symphony of its birth. Picture the universe not as the star-filled expanse we see today, but as a seething, glowing plasma, a cosmic soup so dense and hot that light couldn't travel more than an atom's distance before being swallowed again. This was the universe just 380,000 years after the Big Bang. Then, in a transformative moment, everything changed. As space expanded and cooled, electrons and protons finally combined to form neutral atoms, releasing a burst of light that had been trapped for eons. That light, now stretched by 13.8 billion years of cosmic expansion, reaches us today as a faint microwave whisper, the cosmic microwave background. It's the oldest photograph ever taken, a snapshot of the universe in its infancy, and it's still ringing with echoes of creation. What makes this glow so extraordinary isn't just its age, it's the story written in its subtle imperfections. If you could zoom in, you'd see the cosmic microwave background isn't perfectly uniform. tiny temperature variations, mere millionths of a degree, ripple across the sky like fingerprints. These aren't random flaws, they're cosmic fossils, the imprints of density variations in the early universe. Slightly denser regions where matter clustered more tightly appear cooler, while sparser regions glow warmer. These fluctuations were the seeds of everything we see today: the galaxies, the voids between them, even the vast cosmic web threading through space. Without those minute differences, gravity would have had nothing to grip, and the universe would have remained a featureless sea of particles. Now here's where it gets musical. When scientists analyzed these fluctuations, they didn't just map structure, they found rhythm. The variations follow a pattern called the power spectrum, a graph of how much structure exists at different scales. Plotting it reveals peaks and valleys that correspond to acoustic oscillations, pressure waves rippling through the primordial plasma, like sound waves in a colossal bell. The positions of these peaks aren't arbitrary. They align with harmonic ratios, the same mathematical relationships that define musical intervals. It's as if the early universe was resonating, its vibrations frozen into the fabric of space-time. Think of it like this: strike a bell and it rings with a fundamental tone plus higher harmonics. The cosmic microwave background shows us the universe did the same. The first peak in its power spectrum, that's the fundamental note, the dominant wavelength of those ancient density waves. The second peak, the octave. The third, a perfect fifth. These aren't musical notes in the traditional sense, they're the universe's way of revealing its underlying structure through the language of waves. And just as a musician tunes an instrument by listening for harmony, cosmologists tune their models by matching these cosmic harmonics to the predictions of quantum physics and relativity. So when we talk about the music of the spheres today, it's not metaphor. The universe really did sing not with sound, but with the physics of vibration, leaving behind a score we can read in the oldest light there is. And as we'll see next, this cosmic symphony holds clues to mysteries far beyond what Pythagoras or Kepler could have imagined. Turning raw cosmic microwave background data into audible music isn't as simple as pressing play on a recording. It's a meticulous alchemy of physics, mathematics, and artistry. Imagine holding a map of the sky where every tiny variation in temperature corresponds to a musical note. Scientists start by taking the Planck satellite's ultra-precise measurements, those minute fluctuations as small as 1 part in 100,000, and scaling them into a range our ears can perceive. Warmer regions might shift to higher pitches, cooler areas to lower ones, transforming the universe's thermal fingerprint into a celestial scale. But how do you decide which note represents which temperature? That's where scaling methods come into play. A linear approach assigns pitches in direct proportion, like a piano where each key steps up uniformly in frequency. This preserves the raw relationships in the data, letting you hear the universe's imperfections exactly as they are. But there's another way, logarithmic scaling, which mimics how human ears naturally perceive sound. Just as a jump from middle C to the next C feels musically equal to a leap from a high C to the next octave, logarithmic scaling emphasizes the ratios between temperatures, revealing harmonies hidden in the numbers. The result, a richer, more resonant translation where the universe's structure sings in intervals our brains are wired to find pleasing. Now, consider the contrast between dense galaxy clusters and the vast cosmic voids. In sonification, these extremes become dramatic musical opposites. A knot of ancient matter, its gravity pulling spacetime into a deeper well, might resonate as a sustained low drone, a cosmic bass note. Meanwhile, a void where spacetime stretches thin and matter is scarce could ring out as a shimmering high tone, almost ethereal. When played together, these contrasts create a dynamic soundscape, mirroring the universe's own tension between emptiness and abundance. The magic truly unfolds when you hear it. One famous sonification assigns the CMB's entire sky map to a 2-minute composition, with Earth at the center and pitches radiating outward like spokes on a wheel. As the audio sweeps around the celestial sphere, you can feel the rhythm of creation, the dense filaments of the cosmic web thrumming like cello strings, the void sighing like wind through a canyon. It's not just data anymore, it's the universe introducing itself in a language older than words. And as we'll soon discover, these sounds aren't just beautiful, they're clues to the very nature of reality. The cosmic microwave background hums with patterns so precise they could have been composed by a master musician. When scientists chart the distribution of its hot and cold spots, they don't just see randomness, they uncover a harmonic architecture, a series of peaks and troughs that follow mathematical ratios eerily similar to those found in music. Take the first major peak in the CMB's power spectrum, representing the most common distance between temperature fluctuations. This dominant wavelength isn't arbitrary. It corresponds to what musicians would call the fundamental frequency, the lowest and loudest note in a chord. The second peak, that's the octave, vibrating exactly twice as fast as the fundamental. The third aligns with a perfect fifth, the interval that forms the backbone of Western harmony. It's as if the infant universe was tuning itself, resonating with the same intervals that human ears have found pleasing for millennia. But why do these particular harmonics dominate? The answer lies in the physics of sound waves racing through the early universe's plasma. Picture the cosmos moments after the Big Bang as a roiling ocean of particles and energy. Tiny quantum fluctuations, random ripples in density sent pressure waves pulsing outward, like drops hitting the surface of a pond. These waves traveled until the universe cooled enough for atoms to form, freezing their patterns into the CMB. The most prominent harmonics we see today are the ones that had just enough time to complete full oscillations before this cosmic freeze frame. Waves that fit neatly into the universe's age at that moment reinforced themselves, creating peaks in the power spectrum. Others, out of sync, cancelled out, leaving quieter gaps. It's the same principle that makes a guitar string ring clearly when plucked at just the right spot. Resonance amplifies certain frequencies while suppressing others. The parallels run even deeper. In music, consonance, the pleasing blend of notes, arises from simple integer ratios. A perfect fifth, for example, vibrates at a ratio of 3:2. Remarkably, the CMB's acoustic peaks follow similar ratios, reflecting the universe's preference for mathematical elegance. This isn't just a quirk of the data, it's a fingerprint of the underlying physics. The early universe behaved like a colossal musical instrument, with gravity pulling matter inward and radiation pressure pushing it outward, creating a back and forth oscillation. The resulting harmonics reveal the balance of these forces, encoded in light that's traveled for billions of years to reach us. Yet there's a twist. While the CMB's harmonics mirror musical intervals, they're far more than aesthetic curiosities. These patterns act as a cosmic tuning fork, allowing scientists to measure the universe's composition with staggering precision. The relative heights of the peaks, for instance, tell us how much ordinary matter, and dark energy filled the early cosmos. It's like deducing the ingredients of a soup by listening to the sound it makes when stirred. The third peak, weaker than the first two, hints at dark matter's gravitational pull, subtly altering the plasma's oscillations. Even the slight flattening of the peaks reveals how space-time itself is shaped, confirming Einstein's predictions about the curvature of the universe. What emerges is a breathtaking realization. The music of the spheres isn't just poetry. The universe does vibrate with mathematical harmony, not in the way Pythagoras imagined, with planets whistling through the void, but in the fundamental oscillations of space-time itself. Those ancient philosophers sensed a truth modern cosmology has now quantified. The cosmos is structured by ratios and resonances that feel eerily familiar, as if the same patterns that govern a symphony also sculpted the stars. And as we listen closer, this cosmic score continues to reveal secrets about where we came from, what surrounds us, and perhaps even where the universe's grand composition is headed next. Pythagoras believed the universe moved to the rhythm of perfect ratios, numbers so fundamental they shaped everything from vibrating strings to planetary orbits. Today, cosmology uncovers something astonishing. Those same ratios are etched into the cosmos itself, hidden in the angular sizes of the cosmic microwave background's fluctuations. Take the most common distance between hot and cold spots on the CMB sky, about 1 degree across. This isn't a random measurement. It's the cosmic equivalent of a musical octave, the interval where frequencies double. Just as a string divided in half produces a pitch 1 octave higher, the universe's dominant wavelength reflects a doubling of scale, a harmonic echo of Pythagoras' ancient insight. Dive deeper and the parallels grow clearer. The second most prominent peak in the CMB's power spectrum aligns with a perfect fifth, the interval Pythagoras revered for its 3:2 ratio. In music, this interval forms the backbone of chords, creating resonance so pleasing it defines entire genres. In cosmology, it marks the distance where secondary density waves reinforced themselves in the early universe's plasma. Even the perfect fourth appears, its 4:3 ratio mirrored in the spacing of galaxy clusters today. These aren't vague resemblances, they're precise mathematical correspondences, suggesting the universe didn't just expand, it composed itself. How could ancient musical intervals govern something as vast as cosmic structure? The answer lies in the physics of resonance. In the moments after the Big Bang, quantum fluctuations sent ripples through the universe's hot, dense plasma. Waves that traveled specific distances before the cosmic freeze reinforced each other, imprinting their preferred scales onto the CMB. Like a vibrating drumhead, the universe favored wavelengths that fit neatly into its age at that moment. The result, a power spectrum with peaks at intervals Pythagoras would recognize instantly, harmonics written not in notes, but in the distribution of matter itself. This harmonic architecture isn't just a curiosity, it's a forensic tool. The relative heights of these peaks reveal the universe's ingredients. The first peak's prominence confirms the dominance of dark matter, whose gravity sculpted the early plasma. The third peak's subtler strength hints at ordinary matter's lesser role. Even the slight deviations from perfect ratios, like a piano slightly out of tune, tell a story. They expose the universe's curvature, the tug of dark energy, and the precise timing of cosmic inflation. What emerges is a profound unity. The same mathematical relationships that govern a vibrating string or a trumpet's blast also shaped the universe's largest structures. Pythagoras heard music in the movement of planets. Today, we see it in the frozen waves of the CMB. This isn't coincidence, it's a testament to how deeply mathematics is woven into reality. From quantum vibrations to galactic superclusters, the cosmos hums with ratios that feel both ancient and eternal. And as we decode these patterns, we're not just studying the universe's past, we're glimpsing the harmonic laws that will guide its evolution for eons to come. Imagine the universe not as a silent void, but as a colossal instrument, one so vast its vibrations shape the very fabric of reality. Space-time itself becomes the medium, stretching and compressing like the skin of a drum, with every galaxy, every ripple of dark matter, adding its own resonance to the cosmic chord. This isn't just a poetic metaphor, it's a startlingly accurate way to understand how the universe evolves. Take expansion, for instance. As space stretches, those primordial vibrations, the ones frozen into the cosmic microwave background, aren't just fading, they're shifting like a song played on a record slowing down. The pitch drops, the timbre deepens, and the universe's sound transforms over billions of years. Now, think about dark energy, that mysterious force accelerating the cosmos's expansion. In musical terms, it's like a hand steadily turning a tuning peg, stretching the strings of space-time thinner and thinner. The result, a universe where the harmonics grow more dissonant over time, the once clear intervals between cosmic peaks blurring as galaxies race apart. Dark matter, meanwhile, acts as the counterbalance, a gravitational anchor that clusters matter into cosmic chords, giving structure to the symphony. Without it, the universe's music would be a formless drone, devoid of rhythm or pattern. Together, these unseen forces tune the cosmos, shaping its harmonies in ways we're only beginning to decipher. But here's the profound twist. This musical model isn't just a clever analogy. It's a mathematical mirror. The equations governing vibrating strings and those describing cosmic inflations share uncanny similarities. Both hinge on waves, resonances, and the interplay of tension and release. When physicists simulate the early universe, they don't just crunch numbers, they trace oscillations that behave like sound waves in an impossibly vast instrument. The difference, instead of wood or metal, the materials are space, time, and quantum fields. And the notes produced aren't mere vibrations in air. They're the seeds of galaxies, the blueprint of everything we see. What does this mean for the future of the Cosmic Symphony? As dark energy keeps pulling space apart, the harmonies born in the Big Bang will grow fainter, their wavelengths stretched toward silence. Yet even then, the music won't disappear entirely. Like an echo lingering in a cathedral long after the choir has stopped singing, the universe's original vibrations will remain encoded in the distribution of matter, the curvature of light, and the slow dance of galaxies. To study cosmology, then, isn't just to map the stars, it's to listen for the faintest traces of a song 13.8 billion years in the making. One that tells us not just where we came from, but how the cosmos itself chooses to resonate. Stretching across billions of light years, the cosmic web weaves the universe into an intricate tapestry of galaxy clusters, wispy filaments, and vast, empty voids. But this isn't just a static arrangement. It's a dynamic, vibrating structure where every element hums with its own unique frequency. Picture galaxy clusters as dense knots in this cosmic net, each one acting like a massive tuning fork. As galaxies orbit within these clusters, their gravitational pull creates ripples in the surrounding dark matter, sending vibrations echoing through space. These aren't random tremors, they follow predictable patterns, resonating at frequencies dictated by the cluster's size and mass. Scientists have even detected these oscillations in places like the Coma cluster, where the collective motion of thousands of galaxies produces a deep, rhythmic pulse, a bass note in the universe's symphony. Between these clusters lie the voids, unimaginably vast regions nearly devoid of matter. Far from being silent, these cosmic deserts function like the hollow body of a guitar, amplifying and shaping the vibrations passing through them. When density waves from nearby clusters travel into a void, they stretch and rebound, creating standing waves that linger like echoes in a canyon. Recent simulations reveal how these voids can ring at specific frequencies, their emptiness acting as a resonating chamber that subtly distorts the light of galaxies beyond them. It's as if the universe carved out these hollows not just to separate matter, but to give space itself a voice, Then there are the filaments, those delicate threads of dark matter and gas connecting clusters like bridges of shimmering silk. These aren't passive highways for galaxies. They vibrate like plucked strings, their oscillations governed by the tension of gravity and the push of dark energy. Astronomers studying the Sloan Digital Sky Survey have mapped subtle vibrations along these filaments, finding patterns that match predictions from quantum physics. Some vibrate at frequencies corresponding to the same harmonic intervals found in the cosmic microwave background, as if the universe's earliest chords still reverberate through its largest structures. What would Pythagoras make of this? His vision of celestial harmony revolved around perfect geometric shapes and musical ratios, ideas dismissed as mystical for centuries. Yet here we are, discovering that the universe's grandest structures dance to rhythms that mirror his ancient intuitions. The cosmic web doesn't just organize matter, it sings with the same mathematical elegance he revered. Those filaments and voids aren't random chaos, they're the universe's way of tuning itself, a resonance spanning from the quantum flickers of the Big Bang to the gravitational hum of superclusters. And as we listen, we're not just mapping the cosmos, we're hearing the echoes of a harmony written into the laws of physics themselves. Let's press play on the universe's oldest recording. When scientists sonify the cosmic microwave background, the result isn't just noise, it's a haunting chorus of creaks, hums, and pulses, each one a direct translation of the Big Bang's afterglow. Close your eyes and listen to the first few seconds, a deep, resonant drone, almost like the lowest note on a pipe organ. That's the universe's fundamental frequency, the dominant wavelength of those primordial density waves frozen in time. Then comes a shimmering rise, a cluster of higher pitches flickering in and out. These are the smaller fluctuations, the quantum ripples that seeded galaxies. Together, they form a soundscape both alien and strangely familiar, like a storm heard from underwater. Now focus on the rhythm. Beneath the surface noise, there's a pulse, a slow, steady beat marking the peaks in the CMB's power spectrum. That recurring thump corresponds to the universe's first acoustic oscillations, the pressure waves that bounced through the plasma like echoes in a cavern. The timing between these beats isn't random. Listen closely, and you'll hear intervals mirroring musical chords, a perfect fifth here, a major third there. These harmonies aren't artistic embellishment, they're mathematical truths. The same ratios Pythagoras discovered in vibrating strings govern the spacing of galaxy clusters today. What makes these sounds so valuable to scientists? Our ears detect patterns our eyes might miss. In visual data, the CMB's temperature variations look like static, a scatter of hot and cold spots. But when converted to audio, their structure becomes visceral. A sudden spike in pitch might reveal a dense knot of dark matter, while a prolonged low tone traces the gravitational well of a nascent supercluster. Astronomers have even identified cosmic discordances, notes that fall slightly out of tune with predictions. These anomalies hint at physics beyond our current models, like undiscovered particles or exotic dark energy behavior. One of the most startling moments in the sonification comes around the halfway mark, a dramatic swell, then silence. That's the imprint of recombination, the moment atoms formed and light broke free. The swell represents the final, frantic vibrations of the plasma, while the silence that follows marks the birth of the transparent universe. It's a sonic fossil of the cosmos's first breath, a pause that literally changed everything. Hearing the universe this way does more than satisfy curiosity. It rewires how we perceive cosmic history. Those eerie tones are the vibrations of space-time itself, a direct line to an era when the entire cosmos could fit in a speck smaller than an atom. And as technology advances, we're not just listening to the past, we're composing a new understanding of reality, one note at a time. To understand the universe's hidden symphony, we need a mathematical instrument, one that can sift through the cosmic microwave background's seemingly random noise and extract its underlying harmonies. Enter Fourier analysis, the same tool musicians used to break complex sounds into pure tones. Imagine holding a tuning fork to the sky, not to listen but to measure. Fourier transforms do exactly that, decomposing the CMB's temperature variations into a spectrum of frequencies, revealing which notes dominate the cosmic chorus. The process is like isolating individual instruments in an orchestra, separating the deep thrum of dark matter from the shimmering resonance of primordial plasma waves. The result of this analysis is the power spectrum, a graph cosmologists treat as the universe's sheet music. On the horizontal axis, you see angular scales, the size of temperature fluctuations on the sky. The vertical axis shows their intensity, how much those fluctuations deviate from the average. The peaks in this graph aren't random spikes, they're precise harmonics, each corresponding to a preferred scale of vibration in the early universe. The first peak, tall and commanding, marks the fundamental frequency, the dominant wavelength of density waves that had just enough time to compress and rarefy before light broke free. The second peak, an octave higher, captures waves that completed 2 full oscillations. Together, they form a cosmic chord, a fingerprint of the universe's resonant structure. But here's where it gets even more fascinating. These peaks don't just mirror musical intervals, they encode the universe's ingredients. The height of the first peak reveals how much ordinary matter and dark matter clumped together under gravity's pull. The second peak's position tells us about the speed of sound in the primordial plasma, while the third peak's subtle rise hints at the interplay between matter and radiation. It's as if the cosmos left us a recipe written in harmonics, and Fourier analysis lets us read it note by note, zoom out, and these mathematical patterns manifest in the real universe's structure. The same harmonics that appear in the CMB's power spectrum govern the spacing of galaxy clusters today. Regions where density waves reinforced themselves became the seeds for superclusters, while the troughs between peaks evolved into vast voids. The universe didn't just expand, it vibrated, and those vibrations etched themselves into the distribution of matter we see now. When astronomers map galaxies, they're essentially tracing the echoes of those primordial notes, still resonating billions of years later. This discovery carries profound philosophical weight. Pythagoras believed numbers were the language of the cosmos, and modern cosmology confirms it, not as metaphor but as fundamental truth. The fact that the same mathematics describing a vibrating string also governs the universe's largest structures suggests an astonishing unity in nature's laws. Whether it's the harmonics of a violin or the oscillations of space-time, reality seems to follow a hidden score, one written in ratios and resonances. That raises a tantalizing question. Is this musicality a coincidence, or does it point to something deeper about how the universe chooses to structure itself? The answer might lie not just in the equations, but in the very nature of existence. Pythagoras stood in the shadows of his secretive school, tracing geometric shapes in the sand as he taught his followers that the planets moved to silent harmonies, perfect intervals only the enlightened could hear. 2 millennia later, Johannes Kepler crouched over candlelit manuscripts, scribbling musical notes beside planetary orbits, convinced each world sang a distinct pitch based on its speed. Both men envisioned a universe governed by musical mathematics, yet neither could have dreamed how eerily close to the truth they were. Today, as cosmologists analyze the cosmic microwave background, they're uncovering harmonies that mirror these ancient visions, not in planetary motion, but in the very fabric of spacetime. The Pythagorean model relied on spheres nested within spheres, each celestial body's orbit resonating like a plucked string. Mercury, moving fastest, was assigned the highest pitch, Saturn, slowest and most distant, the deepest drone. While we now know planets don't produce audible sound, the underlying idea that cosmic motion follows mathematical ratios was shockingly prescient. The CMB's power spectrum reveals peaks spaced at intervals resembling Pythagorean scales, particularly the octave and perfect fifth. What the ancients missed was the medium. It's not planets singing, but the universe itself vibrating through quantum fluctuations frozen in light. Kepler took it further. His Harmonics Mundi assigned precise musical intervals to planetary orbits based on their elliptical speeds. When modern scientists translated the CMB's temperature fluctuations into sound, they found similar intervals, but with a twist. Kepler's ratios were rooted in observed orbital velocities, while the CMB's harmonics emerged from acoustic waves in the primordial plasma. Both systems, though separated by centuries, share a profound truth. The universe organizes itself through mathematical relationships that feel musical because they're built on the same wave physics that govern sound. Yet the ancients had limitations. Without telescopes or satellites, they couldn't perceive the true source of cosmic harmony, the quantum ripples of the Big Bang. Their models were Earth-centric, focused on visible planets, while today we study vibrations spanning the entire observable universe. What Pythagoras imagined as celestial lyres and Kepler heard as planetary choirs, we now see as oscillations in spacetime's curvature, patterns so vast they shape galaxy clusters. The cultural impact of this convergence is profound. For centuries, the music of the spheres was dismissed as poetic fancy. Now, it's reborn as a scientific metaphor, one that bridges art and physics. Composers create symphonies from CMB data. Philosophers debate whether mathematical beauty drives cosmic structure. The universe, it seems, sings not with literal sound, but through a deeper resonance, one that connects the intuition of the ancients to the algorithms of modern cosmology. And as we listen, we're reminded that some truths echo across time, waiting for the right moment to be heard. From the temples of ancient Greece to the meditation halls of India, humanity's fascination with cosmic harmony transcends time and culture. The Greeks weren't alone in hearing music in the heavens. Civilizations across the globe wove vibrations into their creation stories, each interpreting the universe's song through their own spiritual lens. Take Hinduism's concept of Nada Brahma, the belief that the divine manifests as sound. Sacred texts describe the syllable Om as the primal vibration from which all existence emerged, a resonance so fundamental it mirrors modern cosmology's quantum fluctuations. Similarly, Tibetan Buddhist monks chant in harmonic overtones, their voices mimicking the layered frequencies of the cosmos, a living echo of the universe's own multidimensional vibrations. In China, the idea of cosmic harmony was rooted in yin and yang, the balance of opposing forces expressed through music. Ancient astronomers correlated musical pitches with celestial movements, tuning instruments to the yellow bell, a note supposedly derived from the length of the emperor's bamboo pipe when held upright at the winter solstice. This wasn't mere symbolism. It reflected a profound belief that human artistry should align with the rhythms of the heavens. Meanwhile, indigenous Australian songlines trace pathways across the land that mirror star patterns, with each melody acting as both map and creation story, binding earth and sky through vibrational memory. The contrasts between Eastern and Western interpretations are striking. Where Pythagoras and Kepler sought mathematical precision, Eastern traditions often embraced paradox. The Japanese Ma, for instance, values the silence between notes as deeply as the sounds themselves, mirroring the cosmic voids between galaxies. Native American traditions speak of the Great Song, a continuous vibration sung by all living things, while Mayan cosmology describes the gods tuning the universe like a great flute at the dawn of time. Despite these differences, a universal thread emerges, the intuition that creation isn't silent, but alive with resonant patterns. Today, artists and musicians draw direct inspiration from these ancient ideas, blending science and spirituality. Composer John Cage's Atlas Eclipticoles mapped star positions onto musical staffs, while contemporary sound installations like Cosmic Microwave by Rafael Lozano Hema transform CMB data into immersive auditory experiences. Even pop culture echoes this obsession. Films like Interstellar score black holes with pipe organs, and ambient musicians sample the literal sounds of planetary magnetospheres. These works aren't just artistic whims, they're modern manifestations of an age-old impulse to hear the universe speak. What unites these traditions, ancient and modern, is the recognition that vibration isn't just a physical phenomenon, but a bridge between the measurable and the mystical. Whether through the sacred ratios of a Stradivarius violin or the quantum hum of a distant quasar, humanity keeps returning to the same revelation: the cosmos doesn't just move. It sings, and as we'll see next, this harmony isn't confined to myth or metaphor. It's written into the laws of physics themselves. Imagine a concert hall where the music isn't written by human hands but by the universe itself. That's the radical premise behind compositions like Planck, a piece by composer and physicist Domenico Vicinanza, which transforms raw cosmic microwave background data into haunting orchestral arrangements. Using temperature fluctuations from the Planck satellite, Vicinanza mapped each day to point to a musical note. Warmer spots became higher pitches, cooler regions lower tones, creating a symphony directly transcribed from the Big Bang's echo. The result, a slow, undulating melody that feels both ancient and eerily alive, like listening to the universe's heartbeat. This isn't just artistic experimentation, it's a literal translation of cosmic structure into sound, revealing patterns our eyes might miss but our ears instinctively grasp. But how do you turn cold, scientific data into music that resonates emotionally? That's the challenge avant-garde artists like Laurie Spiegel tackled in her Harmonies of the World series. Instead of rigidly adhering to the CMB's exact values, Spiegel used its mathematical ratios as a framework, weaving them into minimalist electronic compositions. She treated the universe's harmonics as a starting point, not a constraint, much like a jazz musician interprets a score. The dissonant clusters in her work mirror the CMB's minor second intervals, those slight deviations from perfect ratios that cosmologists attribute to quantum noise. What emerges isn't just music, it's a dialogue between scientific precision and artistic intuition, where the universe's imperfections become sources of beauty. The process isn't without hurdles. Raw CMB data, when sonified directly, often produces drones or chaotic noise. To bridge this gap, pioneers like astrophysicist Jana Levin collaborate with composers such as Nico Mulley, blending science and artistry. In their dark matter suite, Levin provided the spectral frequencies of black hole collisions, while Mulley orchestrated them into pulsating strings and woodwinds. The key was scaling stretching milliseconds of gravitational wave data into minutes of music, allowing the ear to detect subtle harmonics hidden in the original signal. It's a delicate balance. Stray too far from the data, and you lose the cosmos's voice. Adhere too strictly, and you sacrifice musicality. Some of the most striking fusions come from projects like Cosmic Cycles, where NASA partnered with the National Symphony Orchestra. Here, CMB sonifications synchronize with visuals of deep space phenomena, creating immersive performances where audiences, here galaxy clusters forming. The composition's climax uses the CMB's first acoustic peak, the universe's fundamental frequency, as a pedal tone, over which strings and brass layer intervals from the power spectrum's secondary peaks. The effect is transcendent, as if the orchestra becomes an instrument for the cosmos itself. These collaborations reveal a profound truth. The boundary between science and art is thinner than we think. When composer Terry Riley worked with cosmologist Brian Keating, they discovered that the CMB's harmonics align eerily with raga scales in Indian classical music, a serendipitous overlap between ancient spiritual traditions and cutting-edge astrophysics. Similarly, the Silicon Symphony project at CERN uses particle collision data to generate algorithmic compositions, proving that the universe's mathematical scaffolding inspires across disciplines. What makes these works revolutionary isn't just their novelty, but their ability to make the abstract tangible. A graph of CMB fluctuations might feel clinical, but when rendered as a choir's rising chromatic lines or a piano's resonant overtones, it triggers something primal. We're not just learning about the cosmos, we're feeling it. And in that visceral connection, we glimpse a deeper unity, one Pythagoras dreamed of but never could have quantified. The universe doesn't just whisper its secrets through equations, it sings them if we're willing to listen. The universe doesn't just play music, it performs on a stage so vast, the very scales of its vibrations defy human intuition. Picture a grand piano stretched to the size of a galaxy, its lowest note vibrating not over seconds, but over hundreds of thousands of years. That's the reality of cosmic harmonics. When we talk about the universe's sound, we're dealing with wavelengths that could span millions of light years, frequencies so deep they make the lowest organ pipe seem shrill by comparison. Take the CMB's fundamental tone, the dominant peak in its power spectrum. That single oscillation took nearly 400,000 years to complete, a drawn-out hum echoing across a plasma-filled cosmos. Compare that to a concert A vibrating at 440 times per second, and you start to grasp the staggering difference in scale. Yet the physics remains eerily familiar. Just as a cello's string vibrates at specific frequencies determined by its length and tension, the universe's oscillations follow the same wave mechanics, just amplified to cosmic proportions. The early plasma acted like an unimaginably large instrument, with gravity pulling matter inward and radiation pressure pushing it outward, creating standing waves. The key difference: on Earth, sound travels at around 760 miles per hour through air. In the primordial universe, those pressure waves raced through plasma at over half the speed of light, their colossal wavelengths imprinting patterns we now see frozen in the CMB. Why can't we perceive these cosmic rhythms? It's not just their slowness, it's their sheer size. Human ears detect sounds between 20 and 20,000 hertz, vibrations compact enough to jostle our eardrums. The universe's vibrations, by contrast, operate at frequencies measured in nanohertz, oscillations so gradual they'd take 10 million years just to complete a single cycle. Imagine trying to hear a foghorn that blasts once every ice age. Even if space carried sound, these notes would be eternally below our threshold of perception. This is where technology becomes our translator. Just as microscopes reveal the invisible small, sonification techniques make the imperceptibly slow audible. By compressing billions of years of cosmic evolution into minutes of audio, scientists can shift these ultra-low frequencies up 57 octaves, bringing them into the human hearing range. The result: a galaxy cluster's gravitational waves, which in nature might vibrate once every 10 million years, become a rumbling bass note you can feel in your chest. The CMB's temperature fluctuations, originally spanning epochs, transform into shimmering chords. It's not merely artistic license, it's a crucial tool for discovery. Our ears, honed by evolution to detect subtle patterns in sound, often catch irregularities that eyes gloss over in visual data. A sudden dissonance in the sonified CMB might hint at unknown physics, like dark matter's ghostly interactions or extra dimensions warping spacetime. The next frontier lies in real-time cosmic listening. Projects like the Laser Interferometer Space Antenna LISA aim to detect gravitational waves from merging supermassive black holes, vibrations so low they'd take years to cycle. By converting these space-time ripples into sound, we'll essentially eavesdrop on the universe's deepest registers, a bass line played by collapsing stars and colliding galaxies. What began as Pythagoras' poetic vision has become a scientific revolution, not just studying the cosmos, but hearing it speak in frequencies once reserved for gods and myths. And as our tools grow more sensitive, we're tuning into channels we never knew existed, uncovering rhythms that predate stars themselves. Turning cosmic whispers into audible sound requires more than just pressing a button. It's a sophisticated interplay of algorithms, physics, and artistry. At the heart of this process lies specialized software like Sonify and Sonification Sandbox, tools designed to translate numerical data into rich, layered soundscapes. These programs don't just assign random pitches to numbers, they map the exact relationships within the data, preserving the mathematical integrity of cosmic patterns. Take, for instance, the way they handle the cosmic microwave background. By converting temperature fluctuations into frequency variations, the software ensures that a warmer spot in the CMB doesn't just sound higher, it resonates in precise harmonic proportion to its cooler neighbors, mirroring the universe's own acoustic oscillations. Different sonification methods yield strikingly different results. Linear scaling, for example, treats every increment in the data as an equal step in pitch, like climbing a piano's keys one by one. This approach is straightforward, but it can miss subtle harmonies hidden in the numbers. Logarithmic scaling, on the other hand, mimics how human ears perceive sound, emphasizing ratios over raw values. It's the difference between hearing individual raindrops and the rhythmic patter of a storm. The latter reveals the deeper structure. Some of the most revealing techniques involve granular synthesis, where tiny snippets of sound are layered to represent dense datasets. When applied to galaxy cluster vibrations, this method transforms statistical noise into something resembling a choir, with each grain of sound representing a pocket of dark matter or a filament of gas. The scientific value of these techniques is immense. Astronomers working with datasets like the Sloan Digital Sky Survey have used sonification to identify anomalies in galaxy distributions patterns that might have taken months to spot visually. Our ears are uniquely attuned to detecting irregularities in rhythm and pitch, making sonification a powerful tool for uncovering cosmic outliers. A sudden dissonance in the audio might reveal a previously unnoticed quasar, or a repeating motif could hint at large-scale structures bending light in unexpected ways. In one notable case, researchers sonifying X-ray data from a black hole binary system caught a faint, recurring chirp buried in the noise, a signature of material spiraling into the event horizon at precise intervals. Beyond pure research, sonification has become a bridge between laboratories and living rooms. Projects like Astrosysmology for Everyone let students manipulate stellar oscillation data as if tuning a synthesizer, hearing how a star's internal vibrations change with mass and age. Planetariums now pair sonified CMB maps with immersive visuals, allowing audiences to hear the Big Bang's echo while surrounded by swirling galaxies. Even smartphone apps like Space Sounds translate real-time satellite data into ambient music, turning a walk under the night sky into a live cosmic concert. The magic lies in accessibility. Where equations and graphs might intimidate, sound invites curiosity. A child might not grasp the physics behind a supernova, but when they hear its shockwaves rendered as a crescendo of crashing cymbals and rumbling bass, they feel the scale instinctively. Museums have embraced this, installing interactive exhibits where visitors play the solar system by sliding their hands across touchscreens, each planet's orbit triggering a distinct tone based on its orbital period. These tools don't just educate, they evoke wonder, proving that the universe's song isn't locked away in supercomputers. It's a melody we're all wired to understand, if only we learn to listen. Imagine a high school physics class where students don't just stare at equations on a chalkboard, they feel the universe expanding through sound. This is the power of sonified cosmic microwave background data in education. At the University of Washington, astronomy professor Dr. Emily Levesque transformed her introductory course by having students analyze audio versions of CMB fluctuations before seeing the graphs. The result, a 23% increase in comprehension of inflation theory compared to traditional methods. One student described it as hearing the Big Bang's fingerprint, instantly grasping how quantum ripples stretched into galactic structures when the vibrations morphed from chaotic noise into harmonic intervals. The magic lies in how our brains process multisensory input. Cognitive studies show combining auditory and visual learning activates both the temporal and occipital lobes simultaneously, creating stronger memory pathways. When MIT's Kavli Institute tested this with middle schoolers, students who manipulated sonified dark matter simulations could accurately describe filament structures weeks later, while those relying solely on visuals struggled. Teachers report breakthrough moments, like a dyslexic student who aced a cosmology quiz after identifying CMB peak patterns by ear that he'd missed in textbooks. It's like finally being handed the right decoder ring, said 9th grade educator Carlos Mendez, whose students now build DOI spectrograms from NASA public data sets, overlaying sounds onto 3D printed universe maps. But the applications stretch beyond classrooms. Therapists at Johns Hopkins have begun experimenting with cosmic soundscapes for anxiety relief, finding that slowed-down CMB harmonics stretched to 60 beats per minute induce the same theta brainwave state as meditation. The deep, resonant frequencies mirror the human body's natural vibrations, creating what neurologists call acoustic grounding. Veterans participating in a pilot study reported 40% reductions in PTSD symptoms after sessions listening to sonified galaxy cluster oscillations layered with guided breathing. There's something primal about these sounds, noted lead researcher Dr. Priya Desai. Unlike artificial white noise, they carry the weight of 13.8 billion years, a reminder of our tiny but connected place in the cosmos. This fusion of science and sensation is revolutionizing how we communicate the universe's wonders. Planetariums from Tokyo to Chicago now offer cosmic concerts, where live musicians improvise alongside real-time CMB data streams. In Oslo, a children's hospital project sonified star formation sequences onto ceiling tiles in oncology wards, turning chemotherapy sessions into interstellar journeys. Even corporate teams use these audio visualizations for creative brainstorming, proving that the music of the spheres isn't just teaching us about the universe, it's helping us hear our way toward deeper ways of thinking, healing, and imagining. There's something strangely calming about listening to the deep, resonant tones of the cosmic microwave background, a phenomenon scientists are only beginning to understand. Recent studies in neuroacoustics reveal that when these ultra-low cosmic frequencies are scaled into the human hearing range, they trigger measurable changes in brain activity. At the University of California's Auditory Neuroscience Lab, researchers observed theta-wave synchronization, the same brain rhythms associated with deep meditation, in participants exposed to sonified CMB data. The effect was most pronounced with logarithmic scaling, where the universe's natural harmonic ratios remained intact. It's as if our neural wiring recognizes these patterns, even though the original vibrations predate life itself by billions of years. This discovery bridges modern cosmology with ancient sound healing practices. Tibetan singing bowls, for instance, produce fundamental tones around 110 Hz, a frequency that aligns with the second peak in the CMB's power spectrum when compressed 50 octaves. Both create binaural beats where slightly different tones in each ear induce relaxation. Traditional didgeridoo players in Australia harness similar physics, their instruments droning vibrations mirroring the standing waves found in cosmic voids. Shamans from Siberia to the Amazon have long used repetitive drumming at 4 to 7 beats per second, precisely the theta rhythm range that CMB sonifications now elicit in laboratory settings. The parallels suggest humanity intuitively tuned into nature's resonant patterns long before telescopes revealed their cosmic scale. Anecdotal accounts amplify these findings. At the Hayden Planetarium's Cosmic Sound Bath events, attendees describe out-of-body sensations while immersed in CMB-based compositions. One participant reported, "Hearing the moment when my breathing synced with the universe's pulse," while others cite sudden clarity about long-standing personal dilemmas. These experiences align with the overview effect. Astronauts describe the cognitive shift that comes from seeing Earth from space. Perhaps hearing primordial vibrations triggers a temporal version of this phenomenon, connecting listeners to deep time through sound rather than sight. Yet caution is essential. While cosmic frequencies show therapeutic promise, some entrepreneurs exaggerate claims, marketing Big Bang frequency downloads as cure-alls for diseases, a trend that alarms both scientists and legitimate sound therapists. The key distinction lies in evidence. Peer-reviewed studies focus on stress reduction and focus enhancement, not miracle cures. As neurologist Dr. Amita Patel notes, the CMB's benefit likely stems from its fractal complexity. Our brains evolved to find meaning in natural patterns, whether in waves or woodland streams. This nuanced understanding preserves wonder while grounding it in rigor, allowing us to appreciate cosmic harmonies as both scientific marvel and psychological tool, one that tunes not just instruments, but perhaps the human mind itself. Not everyone hears music in the cosmic static. Some scientists argue that assigning musical meaning to random fluctuations in the cosmic microwave background is like finding faces in clouds, a trick of the human brain wired to seek patterns even where none exist. Skeptics point out that with enough data points, statistical noise can accidentally mimic harmonic intervals, just as a room full of typing monkeys might eventually produce a line of Shakespeare. The eminent physicist Dr. Sabine Hossenfelder has criticized what she calls romanticized cosmology, warning that sonification risks conflating mathematical coincidence with cosmic intent. When pressed, even researchers working with CMB audio admit that turning temperature variations into melodies involves subjective choices, scaling methods that emphasize certain frequencies while downplaying others, like a sound engineer tweaking an equalizer. Yet the counterarguments are compelling. While individual fluctuations might be random, their collective patterns show statistically significant correlations matching acoustic wave theory. Those peaks in the power spectrum aren't arbitrary. They align precisely with predictions from quantum physics about how sound waves would behave in the early universe's plasma. It's the difference between hearing a single random note and recognizing Beethoven's Fifth Symphony in its structured repetition. Teams at Princeton and Cambridge have run Monte Carlo simulations, shuffling the CMB data thousands of times, and found the observed harmonics emerge less than 1 in a million times by chance. The universe's tune isn't just background noise. It's a fingerprint of physics playing out at scales we're only beginning to measure. The real tension lies in distinguishing scientific sonification from artistic interpretation. When NASA releases audio of a black hole's pressure waves, the raw data might span 57 octaves below human hearing, meaning every public sonification is necessarily transposed and compressed. Does that make it less real? Consider how a painter interprets a landscape. The colors are subjective, but the mountains they depict exist. Similarly, while scientists choose how to scale cosmic vibrations into audible ranges, the underlying oscillations are as real as the equations describing them. The artistry comes in making those vibrations meaningful to human ears, not in inventing them wholesale. Alternative theories push the boundaries further. Some cosmologists propose that the universe's harmonics hint at deeper symmetries, perhaps extra dimensions vibrating at frequencies we can't directly perceive, or echoes of pre-Big Bang physics. Others explore quantum gravity models where spacetime itself has a resonant frequency, like a guitar string's fundamental tone. Then there's musical cosmology, a niche field treating the CMB as a literal composition, searching for repeating motifs that might encode information about the universe's origin. While these ideas flirt with speculation, they share a core insight. Vibration isn't just a metaphor for cosmic structure, it's the mechanism. The debate ultimately circles back to a timeless question: is the universe ordered or chaotic? The music of the spheres tradition, from Pythagoras to Planck, argues for an elegant cosmos singing in mathematical harmony. Yet the skeptics remind us that beauty alone isn't proof. Patterns demand rigorous scrutiny. Perhaps the truth resonates somewhere between, in the recognition that while the universe doesn't compose symphonies, its physical laws create rhythms we're only beginning to hear. And as our instruments grow sharper, the line between poetry and physics may prove thinner than we ever imagined. String theory whispers a radical idea that the universe's tiniest building blocks aren't particles at all, but vibrating filaments of energy, each oscillating at distinct frequencies like the strings of a cosmic violin. These theoretical strings, billions of times smaller than an atom, thrum with harmonics that could explain everything from gravity to quantum weirdness. Picture a single string vibrating one way to produce an electron, another way to conjure a photon, its pitch and resonance determining the particle's properties. It's as if the universe composes matter through an unseen symphony with quarks and neutrinos as its notes. This isn't just poetic imagery, the math reveals striking parallels. The equations describing string vibrations mirror those of musical harmonics, with energy levels corresponding to overtones on a guitar string. When physicists talk about superstrings vibrating in 10 dimensions, they're essentially describing a reality where Pythagoras ratios govern the quantum realm. Yet string theory's vibrations differ profoundly from the ancient music of the spheres, where Pythagoras imagined celestial bodies humming as they moved through space, and Kepler assigned them literal musical intervals. String theory's harmonies exist at scales far beyond human perception. There's no audible sound, just multidimensional resonances shaping the fabric of reality. The connection lies deeper in the shared language of mathematics. Both traditions find elegance in ratios, Pythagoras' perfect fifths and string theories, Calabi-Yau manifolds each express nature's love for orderly patterns. Even the concept of branes, membranous structures in string theory that ripple like drumheads, echoes the spherical harmonics of Kepler's planetary orbits, those separated by centuries and scales. Plasma cosmology offers a dissonant chord in this cosmic chorus, rejecting both string theory's tiny vibrations and the CMB's acoustic peaks. It proposes that electrified gas, not gravity alone, sculpts the universe. In this view, galaxy-spanning currents create electromagnetic resonances, with plasma filaments acting as cosmic transmission lines humming with energy. Experiments like the Plasma Cosmology Project have generated miniature galaxy clusters in labs by passing currents through ionized gas, revealing spiral structures eerily similar to those seen through telescopes. While mainstream cosmology dismisses these ideas as fringe, they raise provocative questions. Could electromagnetic harmonics, rather than gravitational waves, explain some large-scale structures? The debate remains unresolved, but it underscores how vibration manifests differently across theoretical frameworks. The cutting edge now blurs these boundaries. Projects like the holometer at Fermilab hunt for quantum noise, in spacetime itself potential evidence that reality is pixelated, vibrating at the tiniest scales. Meanwhile, astrophysicists analyze quasar oscillations for hints of extra dimensions, their flickering light acting like cosmic tuning forks. Perhaps most tantalizing is emergent gravity theory, which suggests gravity isn't fundamental but arises from entangled quantum vibrations, a concept that would make Pythagoras nod in recognition. As we peer deeper, the universe keeps surprising us, revealing harmonies where we least expect them, and reminding us that every scientific revolution begins with listening, not just to data, but to the hidden rhythms beneath. The universe hums at frequencies so low they'd make a subwoofer seem like a tin whistle, vibrations that ripple through space-time itself, carrying secrets from colliding black holes and the birth of galaxies. Recent breakthroughs in gravitational wave astronomy have cracked open this cosmic baseline, with detectors like LIGO and Virgo capturing spacetime's tremors from events billions of light-years away. But these aren't the sharp chirps of merging neutron stars that made headlines. They're the deep, drawn-out groans of supermassive black holes, their orbits so vast that a single wave cycle can last years. To make these ultra-slow ripples audible, scientists compress time dramatically, shifting frequencies up 50 octaves until a vibration that once spanned decades becomes a visceral thump you can feel in your chest. The result, a soundscape where a passing gravitational wave mimics the creak of a ship's hull, and colliding galaxy clusters resonate like distant thunder. Next-generation projects promise to tune us into even deeper registers. The Laser Interferometer Space Antenna, or LISA, slated for launch in the 2030s, will float 3 spacecraft millions of miles apart, forming a gravitational wave observatory the size of Earth's orbit. Freed from our planet's seismic noise, it'll detect frequencies 1,000,000 times lower than LIGO can sense, opening our ears to the slow-motion dances of black holes weighing billions of suns. Early simulations of LISA data turned into sound reveal something eerie. The mergers don't just go bang. They build into crescendos, with orbiting black holes producing spiraling Doppler shifts that sound like cosmic ambulance sirens as they near collision. These aren't just scientific curiosities, they're forensic tools. The precise pitch and timing of these waves encode the black hole's masses, spins, and even clues about the universe's expansion rate. Meanwhile, the cosmic microwave background is getting its own audio upgrade. The upcoming Light Bird satellite, led by Japan's space agency, will map the CMB's polarization with unprecedented precision, hunting for faint B-mode patterns, the telltale swirls left by primordial gravitational waves from the universe's first trillionth of a second. When sonified, these patterns could reveal whether space-time underwent quantum jitters during inflation, a theory that would make the Big Bang's afterglow literally ring with microscopic vibrations stretched to cosmic scales. Other missions, like NASA Spheres, will complement this by scanning hundreds of millions of galaxies for baryon acoustic oscillations, frozen sound waves from the early universe that now sculpt galaxy distributions. Sonifying these vast three-dimensional maps could expose hidden harmonies in the large-scale structure of space, like discovering a celestial rhythm section underpinning everything we see. The most radical proposals push beyond mere translation. Some theorists suggest actively manipulating cosmic data through musical composition, using AI to explore whether the universe's vibrations follow deeper compositional rules. At MIT's Media Lab, researchers trained neural networks on both CMB data and classical symphonies, then generated hybrid pieces where the algorithm completes the universe's themes in musical form. The results blur the line between analysis and art. One generated passage eerily mirrors a Bach fugue structure, hinting that mathematical beauty might bridge human creativity and cosmic patterns. Other teams are designing interactive universe installations where visitors reshape galaxy simulations by singing, literally harmonizing with cosmic evolution. What emerges is a new era of multisensory cosmology, one where we don't just observe the universe but feel its rhythms. As these tools evolve, they could reveal connections invisible to traditional analysis. Perhaps dark matter's distribution follows a vibrational motif, or quantum foam crackles with a stochastic rhythm. The ancients dreamed of hearing the music of the spheres. Today, we're building the instruments to finally play it. And as the data streams in from these next-generation missions, we might discover that the cosmos isn't just singing, it's improvising, with each gravitational wave and CMB fluctuation adding another note to an ever-expanding symphony. What if the universe isn't a three-dimensional space filled with galaxies, but a two-dimensional surface projecting the illusion of depth like a cosmic hologram? This is the startling premise of the holographic principle, a theory born from black hole physics that suggests all the information in our universe might be encoded on its boundary, vibrating like the skin of a drum. Imagine the cosmic microwave background as that surface's resonant pattern, its hot and cold spots not just remnants of the Big Bang, but pixels in a vast cosmic display. The same harmonics we've been decoding, those peaks and troughs in the CMB's power spectrum, could be vibrations on this primordial membrane, their mathematical ratios revealing how information translates from 2D to 3D. It's as if the universe is a symphony performed on a flat sheet, with every galaxy and star merely the projection of its underlying notes. This idea reshapes how we interpret the CMB's music. Those temperature fluctuations aren't just acoustic fossils. They might be bits of data like grooves on a vinyl record encoding a song. When scientists analyze the CMB's patterns using Fourier transforms, breaking them into frequencies like a sound engineer isolating instruments, they're effectively reading the universe's source code. The holographic principle takes this further, suggesting that what we perceive as three-dimensional structure is really a vibrational translation. The CMB's harmonics could be the universe's way of playing back information stored at its edges, with each peak representing a quantum bit vibrating into existence. Recent work at the Perimeter Institute for Theoretical Physics even models this process using string theory, showing how higher dimensional vibrations might project lower dimensional phenomena, much like a hologram's laser light encodes 3D images on a 2D surface. The implications ripple through our understanding of reality itself. If the universe is fundamentally vibrational information, then matter, energy, even space and time might be emergent properties, not primary ingredients. Think of a movie screen. The images seem solid, but they're just light interacting with pixels. Similarly, the holographic principle implies that particles are notes in a grand composition, their properties determined by vibrational modes. This aligns eerily with ancient Eastern philosophies like Advaita Vedanta, which describe reality as Maya, an illusion projected by deeper vibrational truths. Even modern quantum field theory hints at this, with particles being excitations in underlying fields, like waves on a musical string. The difference. The holographic principle suggests those strings aren't just in space, they are space, vibrating at the universe's boundaries. Philosophically, this bridges science and spirituality in unexpected ways. If the CMB's harmonics are the universe's way of tuning itself from 2D to 3D, could consciousness be part of that translation? Some theorists, like physicist Bernard Heisch, propose that subjective experience arises from interactions with these fundamental vibrations, an idea echoing Pythagorean mysticism and Buddhist teachings alike. Others caution against overreach, noting that while the holographic principle is mathematically robust, it's still untested, yet the parallels are tantalizing. Just as a hologram shatters into meaningless fragments if you break it, perhaps the universe's coherence relies on maintaining its vibrational integrity. The CMB, then, isn't just a relic. It's a live broadcast from the edge of reality, a signal we're only beginning to decode. As we stand at this crossroads of physics and metaphysics, one thing becomes clear: the music of the spheres was never just about sound. It's about the universe's deepest language, written in vibrations that shape everything from quarks to quasars. Whether those notes are played on cosmic strings, holographic surfaces, or something stranger still, they remind us that reality is far more malleable and musical than we ever imagined. The idea that the universe hums with mathematical harmonies forces us to confront one of philosophy's oldest questions. Is this order the product of design or an astonishing cosmic accident? When we trace the CMB's harmonic peaks back to quantum ripples in the newborn universe, it's hard not to feel a shiver of awe, as if the cosmos tuned itself with the precision of a master luthier crafting a Stradivarius. Yet science cautions against jumping to conclusions. Those perfect fifths and octaves in the power spectrum emerge from physics, not providence. Gravity and radiation pressure dancing in the plasma of the early universe. But here's the haunting twist: the same ratios that structure galaxies also shape the melodies that move human hearts. Does this mean the universe leans toward beauty, or that we've evolved to find meaning in its chaos? This is where the anthropic principle enters the conversation, the observation that our very ability to ponder these patterns depends on a universe stable enough to produce conscious life. If the cosmic constants had been slightly different, no stars, planets, or ears would exist to hear the music. Some argue this explains the apparent harmony. We're here because the universe's parameters allowed it, like survivors marveling at the improbability of their own existence. Yet others see something deeper: the fact that human minds can decode the CMB's mathematical symphony, that a species which emerged from stardust can grasp the universe's vibrational blueprints, suggests a kinship between consciousness and cosmos. Einstein called this the most incomprehensible thing about the universe, that it's comprehensible at all. Dive further, and you hit the bedrock of metaphysics. Is mathematics the native language of reality, waiting to be discovered, or a human invention we project onto the void? When Pythagoras declared, "All is number," he wasn't just describing nature, he was asserting that numbers exist independently of minds, like Platonic forms. Modern theoretical physicists often work from this assumption, trusting that the universe's harmonies reflect timeless truths. But an alternative view whispers that math is a tool, not a truth, a brilliant but limited lens shaped by our neural wiring. After all, dolphins might devise a wholly different calculus to describe the same cosmic waves. Perhaps the most radical perspective comes from Eastern philosophies, which have long framed reality as vibrational. Hindu texts describe creation arising from Nada Brahma, sound as divine essence, while Buddhist cosmology speaks of reality as an interplay of frequencies. These traditions don't separate observer from observed. The mind that hears the cosmic music is part of the symphony itself. In this light, the CMB's harmonics aren't just data, they're an invitation to dissolve the boundary between scientist and stars, to recognize that the same vibrations orchestrating galaxies also pulse through our cells. The universe doesn't just play music, it is music, and we are its fleeting, grateful listeners. Long before telescopes captured the cosmic microwave background, mystics and sages spoke of a universe built from vibration, an idea dismissed as fantasy until modern physics caught up. Ancient Hindu scriptures described creation arising from Om, a primordial sound reverberating through emptiness, while Hermetic traditions in Egypt taught that the universe is mental, constructed from harmonic ratios. These weren't just poetic metaphors. The Vedas' Nada Brahman, the concept of sound as divine essence, mirrors the inflationary theory's quantum fluctuations, where microscopic vibrations stretched into cosmic-scale density waves. Tibetan monks chanting in multiphonic harmonics unknowingly replicated the CMB's layered frequencies, their deep throat singing resembling the universe's own resonant peaks when scaled to human hearing ranges. Modern spiritual movements have seized on these parallels, interpreting sonified CMB data as evidence of a conscious universe. New Age sound healers use cosmic frequencies derived from Planck satellite measurements, claiming alignment with the universe's original vibration. While scientists caution against conflating data with divinity, the overlap raises provocative questions. Why do sacred traditions worldwide, from Aboriginal songlines to Gregorian chants, share this intuition about vibrational reality? Cognitive scientists suggest it's pattern recognition gone awry, our brains wired to find meaning in randomness. Yet the precision of the CMB's harmonic ratios, matched to Pythagorean intervals with statistical significance, hints that ancient mystics might have glimpsed a deeper truth through contemplation rather than calculation. The key distinction lies in methodology. Science treats cosmic sound as an emergent property of physical laws, measurable and reproducible. Mysticism often inverts this, seeing vibration as the fundamental layer from which matter manifests. String theory oddly bridges both views. Its tiny vibrating strands echo Hindu descriptions of tanmatras, the subtle vibrations preceding physical form. But where spiritual traditions might stop at revelation, physics demands falsifiable predictions. That's why projects like Light Bird Matter, this next-generation CMB mapper, will test whether inflation's quantum jitters left detectable, ringing in polarization patterns, potentially confirming vibrational origins of cosmic structure. What unites these perspectives is wonder. Standing before the CMB's harmonic peaks, a physicist experiences the same awe as a mystic hearing temple bells, a sense of patterns too elegant to be accidental. As we await new data from gravitational wave detectors and quantum gravity experiments, we're left with a humbling thought. Perhaps the universe's deepest truths aren't just seen or calculated, but felt in the gut-deep resonance of a reality that's been singing since the first trillionth of a second. Testing the music of the spheres hypothesis isn't about listening for literal cosmic melodies. It's about hunting for mathematical fingerprints in the fabric of reality. The next generation of cosmic microwave background experiments, like the Simons Observatory and CMB S4, will scrutinize the sky with unprecedented precision, measuring temperature fluctuations down to millionths of a degree. These projects won't just map the CMB's harmonics, they'll test whether those patterns align with predictions from quantum physics and inflation theory. One key target is the spectral tilt, a subtle deviation from perfect scale invariance that could reveal how the universe's primordial vibrations decayed over time. If the tilt matches models where quantum fluctuations generated acoustic waves, it would strengthen the case that the cosmos truly resonates with Pythagorean ratios. But if the data shows unexpected dissonance peaks shifted or missing, it might hint at exotic physics like extra dimensions or unknown dark matter interactions warping spacetime's vibrations. Beyond temperature maps, future missions will focus on polarization, the twisting of light's electric field caused by gravitational waves from the Big Bang. LightBird, set to launch in the late 2020s, aims to detect B-mode polarization patterns, which would act like a cosmic strobe light frozen in the CMB. If these swirls match the harmonic intervals seen in temperature data, it would suggest inflation's quantum jitters really did set the universe ringing like a bell. But a null result wouldn't necessarily silence the music of the spheres. It might mean the instrument was more complex, perhaps multiple fields interacting during inflation, creating a richer, messier resonance. Some theorists even propose that advanced AI could uncover hidden harmonic relationships in existing data, revealing patterns too subtle for human analysis. Negative results would force a reckoning. If the CMB's peaks prove statistically random, or if polarization data contradicts acoustic wave models, the Pythagorean vision of cosmic harmony might revert to poetic metaphor. Yet even then, the underlying mathematics, the way vibrations structure reality from quantum strings to galaxy clusters, would remain profound. The theory's true significance lies less in proving ancient mystics right than in revealing how deeply wave mechanics governs the universe. Whether through confirmed harmonics or revolutionary revisions, these experiments will compose a new chapter in humanity's oldest question: does the cosmos play by musical rules, or are we just hearing patterns in the noise? The answer could redefine not just cosmology, but our very sense of connection to the universe's hidden rhythms. Even in the most harmonious symphony, there are moments of dissonance, notes that clash, rhythms that falter, revealing something deeper about the composition. The cosmic microwave background is no different. While its peaks and valleys largely follow the elegant ratios of musical intervals, scientists have spotted intriguing anomalies, regions where the expected harmonics break down. These cosmic wrong notes might hold the key to understanding forces that shape the universe in ways we never anticipated. One of the most puzzling irregularities is the so-called cold spot, a vast region in the CMB where temperatures dip far lower than standard models predict. Stretching nearly 2 billion light-years across, this anomaly defies easy explanation. Some theorists propose it's the imprint of a colossal void, a bubble of near-nothingness where dark energies push outstripped gravity's pull. Others suggest wilder possibilities: a collision with another universe during inflation, or quantum entanglement on a cosmic scale. What makes these glitches so valuable isn't just their strangeness, it's that they force us to question whether our models of cosmic harmony are incomplete. Then there's the hemispheric asymmetry, a curious lopsidedness where one half of the CMB sky shows stronger temperature variations than the other. It's as if the universe's volume knob was turned up unevenly during its first moments. This imbalance challenges the cosmological principle, the bedrock assumption that the universe looks roughly the same in all directions. Could it hint at pre-inflationary scars, remnants of a chaotic era before space-time smoothed out? Or does it point to something more profound, a fundamental anisotropy woven into the fabric of reality itself? Even the CMB's harmonic peaks aren't perfectly aligned. The third peak, corresponding to a cosmic perfect fifth, appears slightly weaker than predicted. This subtle deficit might betray the presence of unseen particles, sterile neutrinos, or actions that subtly altered the early universe's acoustic oscillations. Alternatively, it could reflect the ghostly influence of dark matter, whose gravitational tug may have dampened certain vibrations like a hand muting a guitar string. These deviations aren't flaws in the data, they're breadcrumbs leading toward physics beyond the standard model. The hunt for cosmic dissonance isn't about disproving the universe's musicality, it's about uncovering its full complexity. Just as jazz musicians use discord to create richer harmonies, the CMB's anomalies may reveal deeper layers of cosmic structure. Future missions like CMB S4 will scan for finer irregularities, while AI-driven analyzers could uncover hidden patterns in existing data. What we're really searching for isn't just answers, but better questions, ones that might resonate through the next century of discovery. After all, the most transformative breakthroughs often begin not with harmony, but with a single, jarring note that refuses to be ignored. At the quantum level, atoms vibrate with precise frequencies, their electrons dancing in orbital patterns that resemble standing waves on a plucked string. These microscopic oscillations determine everything from chemical bonds to the color of light a substance emits. Now zoom out to the cosmic scale, where galaxy clusters hum with gravitational resonances, their movements dictated by the same wave mechanics that govern those atomic vibrations. The eerie similarity isn't coincidence, it's a testament to nature's love for harmonic patterns, repeating across scales from the infinitesimal to the infinite. When physicists study the spectral lines of hydrogen, the notes it emits when electrons jump between energy levels, they're analyzing the same mathematical relationships that describe the spacing of superclusters in the cosmic web. It's as if the universe composes itself through variations on a single vibrational theme. This symmetry between micro and macro reveals itself in unexpected ways. Take the hydrogen atom's emission spectrum. Its wavelengths form ratios matching the intervals of the ancient Greek Dorian mode, a musical scale Pythagoras considered divine. Centuries later, we find those same ratios in the cosmic microwave background's acoustic peaks, like finding a familiar melody played simultaneously on a piccolo and a pipe organ spanning light years. Even chaotic systems echo this order. The fractal branching of river deltas, the spiral arms of galaxies, and the dendritic growth of neurons all follow power laws where complexity emerges from simple repetitive vibrations. Nature seems obsessed with resonant patterns, iterating them across dimensions. Could music be the hidden bridge between these realms? Composers like John Cage intuited this connection when they translated star maps into sheet music, while physicists like Max Tegmark argue that mathematics music's foundation isn't just a tool for describing reality, but reality's fundamental substance. The periodic table's elements arrange themselves by atomic vibration frequencies, just as planets orbit at resonant distances from stars. Some theorists propose that these parallels hint at a deeper truth. Vibration isn't just a property of the universe, it's the mechanism by which information structures existence. From string theory's tiny oscillating filaments to the B-mode polarization patterns in the CMB, reality appears to compute itself through harmonics. This perspective dissolves traditional boundaries. a jazz musician improvising over chord changes and a cosmologist analyzing baryon acoustic oscillations are both decoding vibrational languages, one emotional, the other mathematical, yet rooted in the same physics. When indigenous cultures speak of songlines mapping the land and sky, they're articulating an intuition modern science now quantifies, that the universe organizes itself through resonant relationships. The difference lies in framing. Where science measures frequencies, art feels them. Perhaps the most profound implication isn't about the cosmos, but our place within it. The carbon in our bones, forged in stellar furnaces, vibrates at frequencies resonant with the CMB's ancient hum. Our ears evolved to detect pressure waves in air because those vibrations carried survival information, but they also let us hear Bach's fugues and crashing ocean waves. In this light, music isn't just an art form, it's an evolutionary echo of the universe's harmonic nature, a sensory bridge between quantum flutter and galactic roar. As we continue probing cosmic mysteries, from dark matter's gravitational bass notes to quantum foam's high-frequency crackle, we might discover that the music of the spheres was never metaphorical. It's the soundtrack of existence itself, playing on endless loop from Big Bang to heat death, and we, improbable listeners, are finally learning to sing along. The next decade promises to transform our understanding of cosmic harmonies, with instruments so sensitive they could detect the faintest whispers from the dawn of time. The James Webb Space Telescope, already revealing unprecedented details about early galaxies, will soon be joined by even more advanced observatories like the European Space Agency's Pluto mission, a fleet of 26 robotic telescopes designed to hunt for Earth-like planets by measuring the subtle vibrations of their host stars. These stellar oscillations, akin to seismic waves on a cosmic scale, encode secrets about planetary systems in much the same way the CMB's peaks reveal the universe's infancy. Meanwhile, the Square Kilometre Array radio telescope, set to come online in the late 2020s, will map hydrogen distribution across billions of light years, effectively turning the cosmic web into a resonant chamber where density waves from the Big Bang still linger. But the real game-changer lies in quantum acoustics, a fledgling field merging quantum computing with sound analysis. Researchers at MIT and CERN are developing algorithms that can process gravitational wave data in real time, isolating harmonic patterns that traditional methods might miss. Imagine an AI trained on both Bach cantatas and LIGO black hole mergers, identifying musical structures in spacetime ripples. Early tests have already uncovered unexpected rhythmic regularities in colliding neutron stars, suggesting their final orbits sync up like dancers in a cosmic waltz. These tools won't just listen to the universe, they'll compose its hidden melodies into something we can intuitively grasp. Citizen scientists are about to become vital collaborators in this sonic exploration. Distributed computing projects like Email Protected already let volunteers lend their idle computers to analyze radio signals from space. The next phase, dubbed Cosmic Choir, will invite participants to classify sonified data from telescopes, identifying harmonic anomalies through interactive apps that feel more like music production software than research tools. Picture tweaking a cosmic equalizer to highlight a suspiciously regular pulsar signal, or blending quasar emissions into ambient soundscapes that might reveal hidden patterns. This isn't just crowdsourcing, it's a paradigm shift where millions of ears, trained or untrained, become part of the discovery process. What might we uncover? The most tantalizing possibility involves primordial gravitational waves, the hypothetical vibrations from inflation's first moments. If Light Bird or CMB S4 detects their signature in the CMB's polarization, It could confirm that the universe began as a quantum-scale vibration before expanding into the cosmic chord we observe today. Other targets include dark matter harmonics, subtle distortions in galaxy rotation curves that might betray dark matter's resonant interactions. There's even speculation about multiverse echoes, frequency shifts in the CMB that could hint at collisions with other universes during inflation. As these tools evolve, they'll blur the line between science and art. Composers are collaborating with astrophysicists to create generative music systems where live telescope data influences algorithmic compositions, a fusion of observation and creativity that reflects the universe's own improvisational nature. The ultimate goal isn't just to document cosmic music, but to participate in it, to tune our instruments, both technological and intellectual, to the grand resonance that has been playing since the first moment of time. And in doing so, we might finally answer the question Pythagoras posed millennia ago. If the cosmos sings, what language is it using? The next chapter won't just reveal new notes in the symphony, it could rewrite our understanding of the composer. Turning cosmic data into sound is more than a scientific exercise. It's a delicate dance between discovery and interpretation. While sonification reveals hidden patterns in the CMB or gravitational waves, it also risks projecting human meaning onto phenomena that operate beyond our sensory experience. Take the cosmic scream of a black hole merger. The raw gravitational wave signal, when compressed into audible range, resembles anything from a chirp to a gong depending on scaling choices. This isn't just technical tweaking, it's a form of translation where subtle decisions can shape public perception. Scientists walk a fine line between making the universe accessible and unintentionally suggesting it sings with intentionality. After all, the ratios we call harmonies are mathematical coincidences emerging from physics, not evidence of some celestial composer. Responsible science communication requires transparency about these artistic liberties. When NASA released the sonified sound of the Perseus black hole's pressure waves, headlines proclaimed, "Listen to the roar of a black hole," ignoring that the original frequencies were 57 octaves below human hearing. Such dramatizations, while engaging, risk conflating metaphor with literal truth. The challenge: to harness the emotional power of cosmic soundscapes without obscuring their purely physical origins. Initiatives like the Sonification Toolkit for astronomers now include ethics guidelines, urging researchers to disclose processing steps alongside audio releases. The goal isn't to drain wonder from the cosmos, but to ground it in clarity, helping audiences marvel at real phenomena without attributing mystical qualities to mathematical patterns. Cultural narratives add another layer of complexity. The idea of universal harmony carries weighty historical baggage, from Pythagoras' elitist belief that only philosophers could hear the music of the spheres to colonial-era misuse of natural order rhetoric. Indigenous cosmologies often frame celestial vibrations as relational songs connecting land, sky, and community rather than abstract equations. When Western science appropriates terms like Cosmic Symphony without context, it can unintentionally erase these nuanced perspectives. Projects like the Maori-led Tikoki, the sound model inclusive approaches, blending CMB data with traditional chants to explore resonance across knowledge systems. The lesson: cosmic sonification thrives when it acknowledges its cultural footprint, inviting dialogue rather than asserting dominance. As we near this journey's end, consider how these ethical threads intertwine. The universe's vibrations aren't music, yet in translating them, we inevitably filter them through human ears and histories. That tension isn't a flaw, it's an opportunity. By embracing both the rigor of physics and the humility of interpretation, we can listen to the cosmos not as passive observers, but as participants in a conversation spanning disciplines and generations. The final notes of our exploration won't offer tidy answers, but something richer, an invitation to keep questioning, keep listening, and stay attuned to the universe's unending complexity. Hearing the cosmic microwave background for the first time is like stumbling upon a forgotten lullaby, one that's been humming softly since the dawn of time. I remember the moment vividly, headphones on, eyes closed as the sonified CMB data washed over me. What began as an abstract scientific concept, temperature fluctuations translated into sound, suddenly became visceral. The deep drones, the shimmering highs, the subtle pulses, it wasn't just data anymore. It was the universe introducing itself in a language older than words. There's a peculiar shift that happens when you realize those vibrations aren't just background noise. They're the literal echoes of creation, still resonating in the empty spaces between stars. It makes the cosmos feel less like a distant void and more like a living, breathing entity, one that's been singing all along, waiting for us to tune in. This realization invites a profound question. If the universe vibrates and we're made of stardust, then aren't we too part of that cosmic resonance? Every atom in our bodies, the calcium in our bones, the iron in our blood was forged in stellar explosions billions of years ago. When you listen to the CMB's harmonics, you're not just hearing the past, you're hearing the blueprint of your own existence. Indigenous cultures have understood this connection for millennia. The Aboriginal concept of songlines, paths across the land that mirror celestial patterns, reflects an intuitive grasp of vibrational kinship. Modern physics now quantifies what ancient wisdom sensed, that we're not separate from the universe's music, but participants in it. Try this. Find a quiet space and play a sonified CMB recording at low volume. Close your eyes and focus on the lowest tones, those rumbling frequencies that seem to come from everywhere and nowhere. Imagine those vibrations as threads connecting you to everything, the device in your hands, the air in the room, the distant galaxies whose light hasn't even reached us yet. Notice how your breath syncs with the rhythm, how your heartbeat becomes another percussion in the Cosmic Symphony. This isn't just poetic musing. It's a practice physicists like Brian Greene endorse as sonic mindfulness, a way to viscerally grasp our embeddedness in the universe's fabric. For a deeper exercise, pair cosmic sounds with movement. Stand barefoot and let the CMB's oscillations guide your weight shift, slow, swaying motions as if you're a reed bending to interstellar winds. The goal isn't rigor but resonance, letting your body echo the universe's ancient cadence. Artists like Raphael Lozano Hemmer create interactive installations where participants' movements alter CMB sonifications in real time, blurring the line between observer and performer. These experiences crystallize a truth textbooks can't convey. That science isn't just about observing the cosmos, it's about feeling your place within it. As we near this journey's end, consider how these perspectives reframe our cosmic address. You're not just a speck on a pale blue dot, you're a momentary convergence of stardust, a localized hum in the universe's grand vibration. The CMB's harmonics remind us that order and chaos, vastness and intimacy, aren't opposites, they're notes in the same endless song. Whether through headphones or equations, that song invites us to listen deeper, not just with our ears, but with our bones, our breath, our borrowed starlight. And in that listening, we might just hear the most astonishing truth of all, that the universe doesn't just have music, it is music, and every one of us is a fleeting, glorious chord in its composition. From the ancient dream of celestial music to the precise peaks of the cosmic microwave background, we've traced a story that stretches across millennia, a story where intuition and equations, poetry and physics converge in unexpected harmony. Pythagoras envisioned planets humming in perfect ratios. Kepler scribbled musical notes beside elliptical orbits. Today, satellites like Planck reveal that their visions weren't entirely wrong, just scaled to the universe itself. Those temperature fluctuations in the CMB, when translated into sound, echo the same intervals that define our most beloved chords. The universe doesn't just expand, it resonates, carrying forward the vibrations of its explosive birth like a cosmic echo chamber. What makes this discovery so profound isn't just the science, it's how it bridges disciplines that once seemed worlds apart. The arts and humanities have long explored vibration as a metaphor for connection, from Buddhist chant to Beethoven's symphonies. Now, cosmology provides the empirical backbone. The CMB's harmonics are no metaphor. They're mathematical truths etched into the oldest light we can see, revealing that the universe's structure follows rhythms we instinctively recognize. When a composer writes a melody using the same ratios found in galaxy clustering, or when a sound healer tunes a singing bowl to frequencies mirroring the CMB's peaks, they're tapping into a shared language, one that transcends culture and era. Listen once more to the sonified cosmic microwave background, those deep, resonant tones that began as quantum ripples in a newborn universe. Hear how the fluctuations rise and fall, not randomly, but with a cadence that feels almost intentional. That's the sound of space-time itself, stretched across billions of years and compressed into something our ears can grasp. It's a reminder that science doesn't strip wonder from the world, it amplifies it, offering new ways to experience our place in the cosmos. If this journey has stirred your curiosity, dive deeper. Explore the sonification archives from NASA Chandra X-ray Observatory, or experiment with apps that let you play gravitational wave data. Share your thoughts in the comments. What does the universe's music evoke for you? For those hungry to learn more, links to peer-reviewed papers and interactive tools await in the description. As we close, consider this. Humanity's quest to hear the universe sing is older than telescopes, older than written language. It's a thread connecting the stargazers of antiquity to the physicists of today, all searching for the same truth, that we belong to something vast and alive, humming with patterns we're only beginning to decode. The cosmic microwave background isn't just light. It's a message in a bottle cast across 13.8 billion years, waiting for beings with ears to listen. And in that listening, we don't just study the cosmos, we join its chorus. If this journey through the Cosmic Symphony left you awestruck, you're not alone. There's so much more to explore. Hit that subscribe button and ring the notification bell so you never miss our deep dives into the universe's greatest mysteries. For those hungry to keep unraveling space's secrets, check out our playlist Decoding the Universe, where we break down everything from black hole harmonies to the eerie silence of dark matter. And stay tuned next week. We're venturing into the enigmatic world of neutron-star collisions, where gravitational waves create rhythms sharper than any metronome. But before you go, we'd love to hear from you. Have you ever felt a strange connection to cosmic sounds, whether through meditation, music, or a planetarium visit? Drop your stories in the comments below. We read every one. And if you've ever wondered what the universe might sound like to an alien species, let's brainstorm together. As we wrap up, let's leave you with one last thought. Close your eyes and imagine the deepest note in existence, the hum of the cosmic microwave background, stretched across billions of light years. That's the sound of the universe tuning itself, a vibration so vast it cradles galaxies. Now, as this tone fades into silence, remember, you're not just listening to the cosmos. You're part of its endless, unfolding